All right, let's jump right in. Today, we're going to dive into a world that's totally invisible to the naked eye, but it has a massive, constant impact on our health. Yep, we're talking about the microorganisms in our food. And more importantly, we're going to explore the really clever scientific systems we use to keep an eye on them. We're going on a deep dive to meet the unseen guardians of our food supply, the microbiological indicators that keep us all safe.
So let's kick things off with a fundamental challenge. Just think about the sheer scale of global food production. We're talking billions of meals made, processed, and served every single day. Now, imagine trying to test every single bite of that food for every single potential bug that could make you sick. There are thousands of them. It's impossible. Logistically, financially, you name it. So that brings up a huge question. If we can't test everything, how in the world can we be sure our food is safe? Well, the answer isn't about brute force. It's about being a whole lot smarter.
So to really get our heads around this, here's the roadmap for our explainer. First, we'll lay out the tree scale of the pathogen problem so you can see why direct testing is just not an option. Then we'll introduce the indicator solution, which is this brilliant workaround scientists came up with. From there, we'll actually meet the main players in our key indicator profiles. After that, we'll see how all this science gets put to use in the real world with sanitation in practice. And finally, we'll look at how it all becomes official through food examination and standards. We're going to build this thing from the ground up.
Okay, so let's start by really understanding the mountain we're trying to climb here. Section 1, the pathogen problem. The size of this challenge is exactly why this whole field of indicator microbiology even exists.
This right here is really the heart of the matter. A pathogenic microorganism is just a microbe, a bacterium, virus, or fungus that can make you sick. And trying to hunt down every single one of them in our food supply, it isn't just hard. For all practical purposes, it's impossible. Think about it. We're not looking for one needle in a haystack. We're looking for thousands of different kinds of needles in millions of haystacks every single day. This is the central problem that food safety science was created to solve. So why is it so impossible? Well, it really boils down to 5 big reasons. First, the sheer number of bad guys is just staggering. Second, time. A lot of tests for specific pathogens mean you have to grow them in a lab, and that can take days. By the time you get the results, that food is either already sold or is gone bad. Third, cost. Every single one of those tests costs money. If you multiply that by thousands of pathogens for every batch of food, your grocery bill would be through the roof. Fourth, and this is a really important one, distribution. Contamination is almost never spread out evenly. A pathogen like Salmonella might just be in one tiny spot in a 1,000-pound batch of ground meat. If you don't happen to test that exact spot, you'll miss it completely. And finally, volume. The scale of modern food production is just way too big for that kind of slow one-by-one approach.
So faced with this impossible mission, scientists didn't just throw up their hands. Nope. They developed a proxy system, a really clever workaround. And that brings us to Section 2, the indicator solution. It's all about looking for clues and signals instead of hunting for the culprit directly.
And this definition right here is the key to everything. An indicator organism is a microbe or a group of them whose presence tells us something about the food's history. The classic analogy is the canary in a coal mine. The canary getting sick doesn't tell the miners exactly which gas is leaking, but it screams at them that the conditions are dangerous. It's the same idea here. Finding an indicator doesn't automatically mean a specific pathogen is present, but it's a huge red flag that the conditions that allow pathogens to thrive, like poor sanitation or contamination, have happened. It's a predictive tool that gives us a powerful warning.
And as you can see here, not all indicators are playing the same game. They have 2 totally different jobs. On the left, you've got safety indicators. These are the ones we really care about for public health. They're the ones that suggest a risk of contamination with bugs that can make you really sick. They predict the potential for harm. Then on the right, you have quality indicators. These are more about your experience as a consumer. They predict spoilage. They tell us if the food might taste funky, smell bad, or just not last as long as it should. So finding a bunch of yeast and juice is a quality problem. It might start to ferment, but it's not the same kind of safety alarm as finding an indicator for, say, fecal contamination. Okay, so this leads to a pretty logical question, right? If we're going to put so much trust in these little microbial canaries, how do we pick the right ones? What exactly makes a microorganism a really good, reliable indicator?
This is basically the wish list for the perfect indicator, and each point is super important. First, it has to live in the same place as the pathogen. A lot of nasty foodborne pathogens come from animal intestines, so a good indicator should also come from the gut. That shared origin is the whole reason this works. Next, it's got to be non-pathogenic. This is a huge deal for the lab techs who have to work with these things every day. You don't want the test itself to be a health hazard. Third, it needs to be around in much higher numbers than the pathogen. This just makes it way easier to find. It's easier to spot 100 canaries than one invisible gas leak, right? Fourth, it should grow and survive in a similar way. If your indicator dies off way faster than the pathogen, it's useless. The danger could still be there, but your warning sign is gone. The next two are the holy grail of teamwork. It should always be there when the pathogen is, and never be there when it's not. That way, you don't get false alarms or, worse, miss a real threat. And finally, it has to be easy to spot in the lab with simple, quick tests. That keeps costs down and gets results fast.
But now, it's time for a little reality check. As this quote points out, the perfect indicator doesn't actually exist. There's no single microbe that checks every single one of those boxes. In the real world, food scientists use a handful of different indicators that do a good enough job at meeting most of these criteria to be really effective tools for keeping our food safe. So, that brings us to the actual organisms we use. Let's meet the usual suspects in this microbiological lineup. Section 3, Key Indicator Profiles. First up, one of the most famous groups, the coliforms. So let's break this down. Gram-negative just refers to how they react to a certain lab stain. They're bacilli, so they're rod-shaped, and they don't form tough little protective spores. And their metabolism? Well, they're not picky. They can grow with or without oxygen. But here's their signature move, the thing we look for. They ferment lactose, that's the sugar in milk, and when they do, they produce acid and gas. And that gas production is literally what scientists look for in a test tube. A tiny bubble is a positive result. Finding coliforms, especially in foods that are ready to eat, is a big red flag that something went wrong with sanitation or processing. And inside that big coliform group, there's one member that's especially well known. You might even say infamous. And that is Escherichia coli, or as you probably know it, E. coli. Now, what's really wild about E. coli is that it's got this total Jekyll and Hyde thing going on. On one hand, most strains are completely harmless. They live in our guts right now. They actually help us out by making vitamin K and keeping more dangerous bacteria from moving in. But on the other hand, you've got these specific strains, like the notorious O157H7, that are incredibly dangerous and can cause severe food poisoning. So it's super important to remember, when we talk about E. coli as an indicator, we're usually talking about the common, harmless type that's just signaling a problem. And this is exactly why it's such a superstar indicator. E. coli is considered the gold standard for showing fecal pollution. Because it naturally lives in the intestines of warm-blooded animals, finding it in food or water is pretty much undeniable proof of contamination with fecal matter. And if it's fecal matter, then any other pathogen that lives in the gut, like Salmonella, could be there too. Its presence is a powerful, direct signal of a serious breakdown in sanitation. Let's look at a perfect, real-world example. Pasteurized milk. The entire point of pasteurization is to heat the milk enough to kill off harmful bacteria, including E. coli. So you should never, ever find E. coli in finished pasteurized milk. If a lab does find it, it's like a detective finding a crucial clue. It points to one of three failures. 1, the pasteurization process wasn't done right. 2, the general hygiene in the plant is bad. Or 3, and this happens a lot, the milk was clean but got contaminated after it was pasteurized, maybe from a dirty valve or filling machine. Okay, now let's zoom out to a bigger group. The Enterobacteriaceae is a whole family of bacteria. It includes our friends the coliforms, but also a bunch of other important ones, including big-time pathogens like Salmonella. The main difference in testing for them is that they're identified by their ability to ferment glucose, which is a more common sugar than lactose. Their growth often produces those really foul smells we associate with spoiled meat. In Europe especially, this whole family is used as a wider-angle indicator of overall food quality and hygiene. Now let's switch things up a bit. Everything we've talked about so far has been gram-negative bacteria. But there's another really important group of indicators that are gram-positive, the fecal enterococci and streptococca. So you might be asking, why do we need another indicator if we already have E. coli? Well, these guys have some pretty cool superpowers. First, they don't really multiply in water, so their numbers give you a better snapshot of the original contamination event. But more importantly, these guys are tough. They're way more resistant to stress, like heat, salt, and even disinfectants like chlorine, than coliforms are. This toughness means they can stick around for a lot longer. So even if the E. coli has already died off,
these hardier enterococci might still be hanging around, basically leaving behind a historical record that something bad happened.
And finally, let's talk about a completely different kingdom of life, fungi, specifically yeasts and molds. Now, these are almost always used as quality indicators, not safety indicators. They're incredibly resilient and can grow in all sorts of conditions. Finding them doesn't usually mean there are pathogens around, but it does mean there are probably problems with how the food tastes, smells, or how long it'll last. For example, finding yeast in jam could mean the product is going to spoil or ferment on the shelf.
Okay, so we've met the indicators. Now what? How do we actually use this knowledge in the real world to stop them from showing up in the first place? That brings us to Section 4, Sanitation in Practice. Basically, building a fortress against these microbes. First things first, we have to get this straight. Cleaning and sanitation are not the same thing. Cleaning is about physically removing the gunk you can see, food bits, grease, dirt. It is always step one. Sanitation is what you do after cleaning. It's the step that actually reduces the number of microorganisms down to a safe level. And the order is absolutely critical. Why? Because you can't sanitize a dirty surface. It's that simple. All that physical grime acts like a shield, protecting the bacteria from the sanitizer, making it totally useless. You have to clean first, then you can sanitize.
And this whole process is broken down into a super meticulous 7-step procedure. Let's walk through it. Step 1, inspection and prep. Taking equipment apart so you can get to every nook and cranny. Step 2, sweeping and flushing. Getting rid of the big chunks of debris, then rinsing with warm water. And notice it says warm, not hot. That's because hot water can actually cook things like protein onto the surface, making them even harder to get off. Step 3, washing with detergent to break down all that soil and grease. Step 4, a super important rinse with clean water. Why is this so important? Because any leftover detergent can actually neutralize the sanitizer you're about to use, making the next step worthless. So step 5 is the actual sanitizing, using things like heat or chemicals to kill the microbes. Step 6 is the final rinse or air dry. And finally, step 7, validation, the final check. You look to make sure it's visually clean, and you take microbial swabs to make sure the counts are low. It's the last step to make sure the fortress is secure. All of this work, understanding the indicators, following the sanitation steps, it all leads to one final stage, proving it worked. This is where we get the final verdict on whether a food is safe. Section 5, Food Examination and Standards. You know, when we're deciding if food is good, most of us just use our eyes and nose, right? That's physical examination. If milk smells sour, we toss it. But in the food industry, that's not nearly enough. They also do chemical examination to look for things like toxins. And of course, what we've been talking about this whole time, microbiological examination. That's the only way to see the invisible world of bacteria and fungi we've been discussing. This lab testing isn't just done randomly. It follows a very clear, structured process. First, the lab figures out why they're testing. Is it just a routine check, or are they investigating an outbreak? Then they document the type of food and what the known risks are. They pull up all the rules, and then they take samples to test. Back in the lab, they run the tests to find, count, and identify what microbes are there. And then comes the final crucial step. They compare their results against the official standards to make the call, pass or fail. And to do all this work, labs have a whole toolbox of scientific methods. This isn't all of them, but it gives you a good idea of how serious this all is. You've got methods like pour plates and spread plates to grow and count bacteria. The multiple tube method is the classic way to spot coliforms by seeing if they produce gas. And more, these are being backed up by advanced molecular methods and all sorts of biochemical tests to get a precise idea on whatever's there. So who actually makes up these rules and standards that the labs test against? Well, that's the job of government agencies. In the US, it's the FDA. In Nigeria, it's NAFDAC. These organizations are the ones responsible for taking all the science and turning it into rules that are legally enforced. They're basically the referees, making sure everyone plays by the same safety rulebook. And here's what those rules can look like in the real world. This is just an example, but you see how black and white it is? For general bacteria or fungi, there might be a very small acceptable limit. But for our key indicators and the really dangerous pathogens, the standard is often 0. The guideline for coliforms, E. coli, and a pathogen like staph is nil, 0, none allowed. This is how that whole complex system of indicators gets turned into a simple, clear pass-fail test. So after all that, we kind of end up back where we started, but now we know a lot more. We've got this incredible, multi-layered system of indicators, sanitation rules, and government standards. It's really amazing when you think about it. But
does it make our food supply 100% perfectly safe? Or is this whole massive effort really about managing risk and just getting that risk down to a level that we all find acceptable? It's definitely something to think about the next time you sit down to eat. Thanks for joining me on this deep dive.